from this lecture, we start studying the actual theory of robotics. So in this, the first thing that we need to understand is the spatial representation of rigid body motion. And rigid body motion involves translation and rotation, right? So how to represent translations and rotations together, that is what we next study. And we begin with the simplest possible thing in rotation, that is 2D rotation, plane rotation. Okay. So consider XY plane and a body in it and a point P on the body with coordinates x and y. Polar coordinates r and alpha, two sets of coordinates related like this. Everybody knows this. Now, what we consider is that the body is rotating about the origin of the frame of reference anticlockwise through an angle theta. Where does the point P go? Along with the body, point P moves, basically goes around this origin to say P prime. And we want to find out its new coordinates, x prime, y prime. So for that, seeing its polar coordinates is very simple. Since the rotation is about the origin, so the r coordinate remains same and the angular coordinate changes from alpha plus theta, right? I think I should use this because otherwise the mouse pointer is not working very well. So with this, it will be perhaps better. So the r coordinate remains as it is, and the angular coordinate changes from alpha to alpha plus theta. Now, as we consider that and try to find out the Cartesian coordinates back x prime y prime, then it will become x times cosine alpha plus theta and r times cosine alpha plus theta and r times sine alpha plus theta. When you open that, you get these two expressions, and when you put these two together like this in a vector, taking the coefficients of x and y in this coefficient matrix, then you get a rotation matrix cos theta minus sin theta cos theta. So this matrix R we will call the rotation matrix, basically because this represents a rotation through an angle theta, and the old position vector of a point maps to the new position vector of the same point after the rotation through this linear transformation. So you say that a rotation can be represented through a linear transformation, the matrix of which happens to be this. So rotation matrix, plane rotation matrix, is a 2 by 2 orthogonal matrix with determinant +1 that you can check. It is orthogonal. This is a unit vector. This is also a unit vector, and these two unit vectors are first column, second column. Both are two unit vectors, and they are orthogonal to each other. So it is an orthogonal matrix, and when you try to find out the determinant of an orthogonal matrix is either +1 or -1. In the case of a rotation matrix, it will be always positive, +1. If the determinant of an orthogonal matrix is -1, then that matrix, that transformation, has an element of reflection also. Okay. Fine. Now this is one way. That is, a rotation matrix is a matrix of this kind. The converse is also true. Any 2 by 2 orthogonal matrix with positive determinant +1, will represent a rotation. Because whatever unit vector you are given, you can always put it as cos theta sin theta with theta as some angle. Okay? And then, since this is an orthogonal matrix, so this will be another unit vector perpendicular to this, orthogonal to this, and any unit vector which is orthogonal to another given unit vector, cos theta sin theta, can always be shown as this or its negative. In the case of +1, it will be this. So whatever orthogonal matrix with determinant +1 is given, the moment you find what is, of what angle theta this element is the cosine, everything else gets settled in its own place. Okay? And that makes sense, because for a 2 by 2 orthogonal matrix, if you put 4 numbers, 4 elements, A, B, C, D, symbolically, that gives you 3 conditions among A, B, C, D. A square plus B square equal to 1, C square plus D square equal to 1, and AC plus BT equal to 0. So these 3 conditions, these 3 equations will uniquely fix one set of values. Okay? One angle basically. So only one parameter is left. So it is a one variable matrix. And through one variable, you can represent a plane rotation, 2D rotation. Okay. Now this is rotation. Now you can rotate it through one such rotation, R1, through another such rotation. Then what happens? Through the first rotation R1, a point P will go to R1P, and it's a pre-multiplication, make note. And therefore, when you implement the second rotation, R2 will pre-multiply. So as a result, you can say that the resultant location of the point will be R2 R1P. That means the composition of the rotation, the 2 rotations together, will give you this R2 R1. Okay, because the point is on this side. So first rotation R1, second rotation R2, and so on. And it is, the multiplication is not commutative. Okay, so R2 R1 is different from R1 R2 in general, but in the case of planar rotations, it will turn out to be the same. Okay, inverse of a rotation will be given by inverse matrix, which in this case will turn out to be transpose as well, because it is an orthogonal matrix. Fine. Now we consider 2D rigid body motion, combining translation and rotation. So you will say that rotate and then translate. So translation, all of us know that each coordinate changes by the corresponding movement. So if the displacement is through dx dy, then the position xy will change through that. If there is a rotation first and then translation, then you will get this. So rotate the body and then translate. So you get this. Fine. Now there is a formulation bottleneck. For example, consider successive rigid body motions. First, this rigid body motion, this rotation, this translation. So you take a body and rotate it, translate it, then rotate it, translate it, and so on. So this is the first rigid body motion, this is the second, this is the third. How will you work out the final one? So for that, what you will need to do is implement this on P, R1P plus T1. That is the resulting point after the first rigid body motion. Now when you implement the second rigid body motion, this thing, this parenthetic thing, R1P plus T1, this whole thing you will have to multiply with R2 and then add with R2. And then you get this large thing under the, within the braces, okay, from here to here. This much. And then you implement the third rigid body motion. So it will be R3 times this plus T3, okay, and so on. Now, if you are asked to work out one rotation and one translation, it will represent this entire rigid body motion together, then that will be troublesome. Because then you have to open all this and then find out something times P plus something in that form. That is something plus P plus something. To be sure, it is possible because resultant R will be, in this case, R3, R2, R1, and resultant P will be, that will be ugly. It will be R3, R2, T1 plus R3, T2 plus T3. Okay. First of all, it will be ugly. Besides, this is only 3. So you can at least write it till this point. Now, when there are 18 such rigid body motions, successive rigid body motions, how to write them? It will be trouble, right? So, I mean, writing, analyzing, anything will become difficult. You need a straightforward representation. Okay. And that straightforward representation has been worked. So, this was the issue. That is, for this, what is the corresponding R and what is the corresponding T for the entire sequence of translations and rotations. The remedy is given by a system of homogeneous coordinates, in which you say that for a point in a plane, rather than using 2 coordinates, we will use 3, xy and a dummy 1. And then you will write xy and a dummy 1. On this side also, for the new coordinates, you will write x prime, y prime and a dummy 1. And then, in order to map this appropriately there, through this RP plus T, you will have 2 by 2 leading block here. See, this is a 3D vector now. This is also a 3D vector. So, for a mapping from 3D vector to 3D vector, you need a 3 by 3 matrix. The leading 2 by 2 part of it is the matrix R, which is familiar, rotation matrix. The 2 by 1 column here is T, which is x and y, 20 x, y. And below this rotation matrix R, there are 2 zeros. And below this column vector T, there is a scalar 1. And this is the homogeneous transformation matrix, which is now representing translation and rotation combined. That is a rigid body motion. If you open it out, you will see this. Right? Now, for the successive rigid body motions, you can write it like this, because now the individual rigid body motion, it is just a pre-multiplication with a matrix, transformation matrix. Okay? So you go on pre-multiplying. So this is the first one. You say T1, which involves R1, T1, 0, 0, 1. Then we multiply with T2, capital T2. This T, capital T2. That is R2, T2, 0, 0, 1, and so on. And you will get the resultant. So this transformation matrix gives you the P to represent rigid body motion, that is rotation and translation together. Now let us do this whole thing in 3D. The 2D rotation, which we earlier considered in XY plane, if you treat that same rotation in the 3D space, X, Y, Z, that Z axis was still there, we did not bother about that. So then what will happen? How do you then map X, Y, Z to X prime, Y prime, Z prime? So you say X and Y map to X prime, Y prime as earlier, and Z does not change. Okay. Now these three linear equations, when you write together, look at this. Now this is the rotation matrix. The old 2 by 2 matrix is sitting here, and the third column and the third row are dummy 0, 0, 1. Because this is now no more rotation about origin, it is a rotation about z axis, which was always the case. So you say that rotation about z axis through an angle theta in 3D space will be represented by this 3 by 3 matrix with this special structure of the third row and third column, and the leading 2 by 2 part will be the old 2D matrix, 2 by 2 matrix. So this is the rotation through an angle theta about the z axis. Similarly, when it is about the x axis, the first column and the first row will be the dummy, and this sequence will be here, right? When it is rotation about y axis, the second column and the second row will be the appropriate unit vector 0, 1, 0, and the other four elements like this will be composed of cosine time. However, make note that in the case of y, the minus sign does not come in the northeast corner, but it comes in the southwest corner, okay, the other corner. The reason is, here it was turning from first axis towards the second axis was positive, that is the rotation about third axis involved turning of things from the first axis towards the second axis through the smaller angle. Here it is other way. From here to here it is a negative. So look at the y rotation. So you will find that z to x turning gives you y, not x to z. Okay, so that is why this is negative. So this you have to keep in mind so that you do not make careless mistakes. Now arbitrary rotations, which are not pure about x-axis, about y-axis, about z-axis, can be composed through compositions of these three. Or there are alternative ways. We will see all of them, or several of them rather. Before that, we complete what we have started discussing. That is, now we get the rigid body motion, combination of translation and rotation in So we need this rotation and translation. So for the homogeneous transformation matrix, now we write it like this. In the case of 2D, this was just xy, this was just x prime, y prime, and this was 2 by 2, this was 2 by 1. That is, capital R was 2 by 2, this was 2 by 1. Now all of these dimensions will become 3. As a result, P prime and P are 3-dimensional vectors. So this long thing is a 4-dimensional vector. X prime, y prime, z prime 1. This is x, y, z 1. This R matrix is a 3 by 3 matrix, which is like this. Okay. So the 3 columns of the 3 by 3 matrix R will basically represent the 3 unit vectors along the coordinate directions of a frame, which is different from the base frame in which the whole thing is described through this particular rotation. Okay. So when you give this rotation to a frame, then it changes its orientation, and from an identity orientation, it takes a different orientation. The 3 unit vectors, the 3 coordinate unit vectors of which are sitting here. This T is the 3D translation matrix, translation vector, Tx, Ty, Tz, and the rest is, the last row is the dummy 0, 0, 0. So this matrix is the homogeneous transformation matrix, which is now 4 by 4. Okay, because in the position vector at the end there is a dummy 1. Now, when you want to compose rigid body motions like this, you go on multiplying like this. Okay, and this you do when each successive rigid body motion is given to you as specified in a fixed frame. Okay, if they are referred to the local frame of the body which itself is moving, then it will be the other way around. Okay, and now this is something which you need to understand a little carefully, and for that we will do this discussion in terms of the rotation only, but then generalization of that is not very difficult. Okay. Uh, so first consider, now you are considering successive rotations about or with respect to rotating frame. So in the case of each rotation being described in the fixed frame, we have seen how pre-multiplication is the standard thing to do, which is obvious. Now, if each successive rotation is specified in the frame, of reference of the body, which itself is moving, which itself is rotating, then what to do? So first, consider a ground frame, G. Yeah. Yes. Consider a ground frame, G, capital X, capital Y, capital Z, and a body frame which is going to rotate, B, X, Y, Z, small x, y, z, like this. So in this fixed big capital frame, we have put a body, we have described a body which has a small letter frame, X, Y, Z. Okay. Initially in the same orientation, both origins coincident. And also consider a point P in the body. The point P is ABC. And this P has coordinates ABC. Right now, in both the frames, its coordinates are same because the two frames are coincident. Now ground remains fixed as expected, and the body rotates about the common z axis, okay, through an angle alpha. So what will happen? This x axis will turn like this, y axis will turn like this, other parts of the body will turn, the point P also will turn, Z will remain in its place because that is the axis of the rotation. Now, after this turning, after this rotation through an angle alpha, the orientation of the frame B, as described in frame G, will become this, because this unit vector turns line now like this, okay, towards this side, like this. Here, it comes here. And this unit vector will turn a little like this. This point P will also turn. Now, since the entire body with its frame is turning, so in the local frame, in the small xyz frame, the representations of the points in the body will not change, but it will change in the fixed frame. Okay. So since the x direction now goes and makes an angle alpha with this, so its unit vector in the ground frame will become cos alpha sin alpha 0. And similarly, this fellow's position, which was earlier 0 1 0, okay, now will become this. Z axis remains same, so this is 0 0 1 as it is. Now you see the picture here. Dashed lines show the xyz coordinates, xyz axis of the ground frame, and solid arrows show xyz directions of the turning frame. Okay. So this much has turned this. Okay. This is alpha, and here this is alpha. So x has turned to alpha, y also has turned to alpha. Description of the point P in the local frame, small xyz frame, remains the same ABC, because the point and the body have turned together. Okay. That remains ABC still. In frame G, it is this. This. Okay. As we have seen, as we saw earlier. Okay. So multiplication with the rotation R1, which is this. Okay. Rotation about z axis. Now, after this first rotation has taken place, if the body has to undergo another rotation through beta about its own x-axis. That is, now we are talking about the successive rotations being described in the frame of the body which itself is rotating. About its own x-axis, if it has to turn through an angle beta, okay, then you know now the x-axis will remain here, y and z will turn about it. So where would point P go now? And what would be the new orientation of this frame BXYZ? Okay. So one way to appreciate that is one way to evaluate it and appreciate it is to take the turning frame bxyz for a while along with point P, the entire body and frame together, see it in the old configuration, take it back to the round orientation. Then the usual rotation like this about the x-axis, you give to that, okay? So, and then bring it back. So take back the frame, take back the frame Bx, Yz and P to original orientation. That is x back to x, y back to y. It will be multiplying with R1 inverse. Then execute the needed rotation. This is local x-axis, about local x-axis, so an angle B. Okay. This, and that will be standard multiplication with R2, right? And then antidote to this, step, okay, here. Get things back through multiplication with R1. Okay. So now you see, this is actually this underlined thing here. This underlined thing here is basically a rotation R2 as seen in the R1 basis. So this is a standard linear algebra stuff of basis change. Okay. So you give it an R2 rotation when the R2 rotation has to be seen in the R1 basis. R1 is the frame of reference, where the body B is in the original first time rotated configuration. And through that transformation, you have to subject this point. Okay. And now you open it, and when you open that, you get R1 inverse R1, which is identity. So that condenses out, and as a result, you get R1 R2. This, okay, applied on BP. That is the original position vector of the point P in the frame itself, in the frame B itself. So that means that when the successive rotations R1 and R2 are specified in the turning frame, rotating frame, then the multiplication, successive multiplications will be post multiplications, not pre multiplications. So this is the sense of it. And the same thing in a more general way, including rotation and translation together, turns out to be like this. When each successive rigid body motion is referred in or specified in the fixed frame, then it is the successive pre-multiplications. When each is specified in the local frame, then it will be successive post-multiplications. And inversion also is very straightforward. So inverse of P will be this, inverse of this whole thing, and this 3 by 3 leading part will be R inverse. It is obvious as the same as transpose, and you will see through either block operations, elementary transformations in block operations, or simply by multiplying this and this matrix and this matrix, and getting identity that in this location in the inverse you will have minus R inverse T. And the sense of this, of course, the last row will be standard dummy 0001, which is this. And this is the physical sense, geometric sense of it is hard to miss, because you see the inverse of the rigid body motion means the restoration of the position and orientation of the body to its old one. Okay? So for that, orientation, which has changed by the through the matrix R, has to be taken back. So the taking back rotation is R inverse, same as R transpose for that matter. Now this translation is an issue. So let us see this. Say we are here. This is a frame of reference. Now we rotate and translate and go to here. Okay. So this is X, this is Y, this is Z. Now we go, this is X, this is Y, this is Z. And the orientation has changed, the position has changed. Now, after we have come there, now what should this represent? By what amount we have to go back, okay, to reach the old configuration. So for that, from this position to this position we want to go back. So this vector, which is basically the negative of the vector by which we have come. So that is why it should be minus of the vector, negative of the vector by which we have come here. But then the last time this vector T was seen from the perspective of this. Okay. Now it has to be seen from the perspective of this. So this vector, as given in this frame of reference, when multiplied with R inverse, will give you this vector as seen from here. And that is why this vector minus T is multiplied with R inverse, which is the same as R transpose. So this will turn out to be the inverse matrix. So for the inverse rigid body motion, this has to be transposed and this has to be negated and be multiplied with R transpose. Going back, and as seen from the changed orientation, okay, changed perspective. So that changed perspective, new perspective is this. Okay. All these things are fine, except that we need to do one more little thing. That is, when studying the 3D rotation, we just made one point, that is arbitrary rotations can be represented through compositions of these three or through some other means. So whichever way you do, you basically represent a 3D rotation with the help of 3 coordinates or with the help of 4 coordinates with one extra condition among them. Only 3 coordinates are independent. That we will do in the next.